Today, we will work out some examples on the topic of quantum liquids and quantum solids. The first example is one in which we are asked to show that the chemical potential typical symbol is mu of a Bose gas is always less than or equal to 0. We know that for a Bose gas, the distribution function has the typical form that is the typical form of the distribution function. Suppose mu is greater than 0. Then what happens? We see that if EI, one of the states energy levels, is such that EI is less than mu, if EI is less than mu, then N of EI will be sigma I Gi by exponential. Now, EI is less than mu, therefore, this is positive, therefore, this is less. So, this will be a negative quantity by kBT minus 1, and therefore, this is less than 1. Therefore, denominator of this expression is negative. That means N of EI is negative, but N of EI is the occupation probability. So, occupation probability cannot be negative. Cannot be less than 0. Therefore, our assumption that mu is greater than 0 is not valid. That is, regarding the value of the chemical potential for a Bose gas, which should either be negative or at most equal to 0. Next, we are asked to determine the temperature dependence of the chemical potential. In other words, the derivative with respect to temperature of mu. In order to do this, we note that we can write this as dou by dou T of f of E divided by now dou by dou T of f of E is sigma I Gi then exponential EI minus mu by kBT minus 1 whole square times d by dt of this. So, minus 1 by k b t square of A minus mu. That will be the derivative. Whereas, if you differentiate FFV with respect to mu, then that will be GI again exponential EI minus mu by KBT minus 1 whole square. Then I have to differentiate with respect to mu, so that gives me again exponential times minus 1 by KBT. So, that will be the value of this derivative. So, the ratio of these two, which is d mu by dt, is this divided by this, which will give me E minus mu by t. And since mu is always less than or equal to 0, this will become positive definite, and E is always 0 or positive greater than 0. Therefore, this will be greater than 0. So, that is the how we determine the temperature derivative of the chemical potential. In the next example, we are asked to discuss what happens, discuss the temperature variation of mu for 0 less than t less than T0, where T0 is the so called Bose-Einstein condensation temperature, which we discussed in the lecture. So, let us say at t equal to 0 k, suppose mu has some negative value. Then we also know that d mu by dt is positive. That means as temperature increases, mu increases. That is, mu increases with temperature. So, as one changes, increases the temperature from absolute 0, as T increases, mu becomes, it also increases. That means it takes negative values approaching 0. So, eventually mu becomes equal to 0. This is what happens at t equal to T naught. This is how we defined T naught. Once it reaches t equal to T naught, since d mu by dt is positive, so that means mu has to stay constant. stays constant at this value for at higher temperatures. That is the temperature variation of mu. Having got the temperature variation of the chemical potential, we are asked to discuss the temperature variation dependence of the specific heat Cv for a Bose gas T less than T naught and also T greater than T naught. We know that the specific heat is the temperature derivative of the internal energy. Therefore, we first determine the internal energy and then differentiate the expression with respect to temperature to obtain the specific heat. The energy is given by 3 by 2 kBT V by lambda cube. This is an expression that we discussed in the lecture G phi by 2 of Z, where G phi by 2 Z is the following expression: 4 by 3 root pi integral 0 to infinity dx x to the power 3 by 2 into 1 by z to the power minus 1 exponential x minus 1. This is the Bose function, which we discussed in terms of the Riemann-Zimmermann zeta function in the lecture, and has the value sigma z to the power L by L to the power P, P equal to phi by 2, and the summation is over L. And Z is e to the power beta mu. So, let us first discuss what happens for the temperature range T less than T naught. Here Z equals 1. T greater than T. Since mu is 0, and therefore G phi by 2 of 1 has the value 1.342. Therefore, the specific heat, hence we can substitute this here, and the specific heat, which is dE by dt, is such that this is NkB into 15 by 4 V by lambda cube into G 5 by 2 of 1. For t less than T naught, in the same way we can get Cv equals Nkb into 15 by 4 V by lambda cube into G 5 by 2 of Z. Minus 9 by 4 G 3 by 2 of Z divided by G half Z. This is got by simple differentiation of the expression for the average energy, total energy. So, this is how we obtain the specific heat, and well, we can write small v in both cases, where V is V by N, the specific volume. So, the variation of the specific heat is shown in figure and looks like this. So, let us plot it as Cv by Nkb and T by T naught. So, this has, when T equal to T naught, it has the value 1. So, this goes somewhat like this and then comes down. So, this has a cusp at T equal to T. This is the theoretical variation of the specific heat of an ideal Bose gas, whereas the observed specific heat variation at the lambda point of liquid helium 2 is more like, this is more or less right, but this goes like this. So, that is more like the observed variation. Of liquid helium 2 for around T lambda. Next example is in the form of a true or false question for a given statement. We are asked to state whether the given statement is true or false and justify the answer. What is the statement? The entropy of a helium-3, helium-4 mixture at T greater than 0 K, but well, we can write it as for 0 less than T less than T lambda. This entropy is only the entropy of the normal component. Normal component of liquid helium-4. This is the statement. Now, the answer is that the statement is true. Now, we have to justify. The justification is, we know that in the two fluid model, according to liquid helium-4 is a mixture of a superfluid and a normal component. We discussed this, it is rho S plus rho N. Now, the superfluid carries no entropy. We saw this when discussing the thermomechanical effect. Now, coming to helium-3, it is a fermion because of the odd number of nucleons, 3. Therefore, for a fermion it obeys Pauli exclusion principle. According to which each state is either occupied or unoccupied. So, the occupation probability is 1. One or 0. Therefore, for the occupied states, the entropy of helium-3 is given by the Boltzmann formula Kb log 1, which of course is 0. Therefore, the entropy of the helium component helium-3 is 0, and the entropy of the superfluid fraction of the helium-4 is also 0. So, the entropy which is of this mixture is only due to this normal component of liquid helium-4. That is the answer.